electrical energy and power. Let's take electrical energy first. Energy is the ability to do work. It's measured in joules, but most often we prefer to use the units of energy to be watt hour or kilowatt hour, and that's because joules can be very, very small. You see, electrical energy represented with W is given as charge times the potential difference or applied voltage. And so we have it, but we know again that Q, which is electrical charge, is current times time. So electrical energy can be V times IT. Current times time times the applied voltage. Again, using from Ohm's law, but we know that from Ohm's law, V is equal to IR. Let's call this equation 1 first. If we substitute this into equation 1, we would have that electrical energy W is given as IR for the V times IT. And that will give us I square RT. Again, we can choose to substitute I instead of V. We know that also, but we know that I itself is V over R. That's making making I a formula here. If that happens, we would have, or just substitute I here, we would have that work will be, instead of I now, we have V over R, all squared, times RT. And this will be V squared over R squared times RT. R eliminates one of the R here. So this gives us V squared over R times T. This is another relationship for electrical energy. So this is the electrical energy relationship, or we can use this, or we can use this. So that's that about electrical energy. Let's take some question on this now. Example 1. A source EMF of 5 volts. So we're given our V 5 volts, supplies a current of 3 ampere, that's our I, 3 ampere, and then how much energy is provided in this time for 10 minutes, that's the time. 10 minutes. Actually, we have to convert this to seconds. That is 10 times 60. And that will be 600 seconds. So the question is, how much energy is provided in this time? So the electrical energy, which is, we use VIT in this case now, VI times time. The voltage is 5. The current is 3. And then times 600. This will give us 15 times 6. So that's the answer for this. So let's look at electrical power. Power is the measure of the rate at which energy is used. You see, electrical power is the rate of using electrical energy. So power is just energy over time. So therefore, if we take each formula we have for energy, we have VIT, we have I square RT, and we have V square over RT. Take each of them and divide it by time, because energy over time, energy over time, energy over time, energy over time. We have different expressions for electrical power. It can be VI, it can be I square R, it can be V square over R. So that's that for electrical power. Let's look at some examples under this. Example 2, how much power is expended in an electric circuit when 60 volts is connected across a 30 ohm resistor? So solution, here we are given that the voltage is 60 volts and the resistance is 30 ohms. So power, which is V squared over R. That's the relationship to use here, since we are given V and R. And that will be 60 squared over 30. This will give us 120 watts. Example 3. What is the power if 350 joules of energy is used over a period of 3 seconds? Here, we are given that the energy is equal to 350 joules and the time is 3 seconds. So we know that power is energy over time. So this will simply be 350 divided by 3. And this will give us 116.67 watts. Series and parallel connection of cells. You see, let's take the first one now. Cells connected in series. When cells are connected in series as shown, the total EMF is the sum of individual EMF of the cell. As we can see here now, we have 4 cells, each one having EMF of E1, E2, E3, E4 respectively. So total EMF will be E1 plus E2 plus E3, then plus E4. If there's a 5th cell connected in series, it will be plus E5. Understand that each cells have their own internal resistance, and that's due to the material with which the cells are made. So any cell has its internal resistance. The total internal resistance also will be the sum of individual resistance of each cell. And so total internal resistance will be the sum of first internal resistance of the first cell plus the internal resistance of the second cell plus the internal resistance of the third cell plus the internal resistance of the fourth cell. And that's what we have here. Cells can also be connected in parallel, as we can see here now. But when connecting cells in parallel, understand that we don't have a relationship to get total EMF when the cells have different EMF. But if their EMF are the same, like we have here now, you see the EMF of this is E. So they have same EMF and same internal resistance. Then we can say the total EMF is just the EMF of just one cell. So if it's 2 volts, total EMF will be just 2 volts. You don't sum them up together. You just say 1/2. That's wrong. It's just 2 volts. But their internal resistance now will be 1/R plus 1/R plus 1/R plus 1/R. So that's how we get their total internal resistance. EMF of a cell. The EMF of a cell is the potential difference across the terminal of the cell when it's not delivering any current and external load. So when it's not delivering current and external load, whatever the voltage is at that point in time, whatever the EMF is at that point in time, that is what we call the EMF. Whatever the voltage or the PD is at that point in time is what we call the EMF. So that's that about definition for EMF. Now, as we look at this circuit below now, we have a cell. This is a cell. I'm just trying to show this to show the internal resistance of this cell. This is internal resistance R of this cell here, and it's connected to an external load or to an external resistor. Then we can say that the EMF of this cell will be the voltage in the external resistor with the voltage drop in the internal resistor. We can take note that this can also be written as I is equal to I into brackets capital R plus small letter R if you factorize the I. Now understand that this E is the cell EMF of the cell. Now again, you see IR gives you the terminal PD. So that's the voltage drop across the external load. We call it terminal PD. Now, you see I small r gives us what we call the lost voltage. The lost voltage. So that's the voltage drop across this internal resistor. So that's that about that. So you can be asked to get maybe lost voltage or the terminal PD. So take note that this is what it means. Lost voltage, and this is what terminal potential difference means. Example 1. A battery of EMF 12 volts. So we are given the EMF to be 12 volts. Is an internal resistance. So we are given the internal resistance to be 1.5 ohms. Is connected to an external resistance of 3 ohms. Calculate the current flowing in the circuit. Okay, so I will say E is equal to I into bracket R plus small r. So E is given as 12 volts is equal to I into bracket. This is given as 3 plus 1.5. So this is given as I times 4.5 is equal to 12. So I will be equal to 12 over 4.5. So this will be given as 2. So this will be given as 8 over 3 ampere. Now let's take the next question after this. The terminal PD. We know terminal PD is equal to I capital R, which will be equal to I is 8 over 3 times the capital R, that's 3. So this will give us 8 volts. If this eliminates this. Then C, the lost voltage. That's I small r, which is given as 8 over 3 multiplied by 1.5. This will give us 4 volts. Because 1.5 here 1, 1.5 here will give us 2. And that will give us 8 over 2, which is 4 volts. Example 2. A battery made up of 2 cells joined in series supplies current and external resistance of 5 ohm. If the EMF and internal resistance of each cell is 0.6 volt and 3 ohm respectively, calculate the current flowing in the external resistor, the terminal potential difference, and the lost voltage. To solve this question, actually, very simple, but I would like to draw out the circuit firstly. So this is it now. The first cell and its internal resistor, and the second cell and internal resistance. So now connected, this is internal resistance, this is the first EMF. Fortunately, they have the same EMFs, 0.6 volts, 0.6 volts, and the same internal resistance. Now connected to an external resistance, which has 5 ohm, which is 5 ohm. This is 3 ohm, and this is 3 ohm. And this is 0.6 volts, and this is 0.6 volts. So this is how it is, just 2 cells. This is the first cell, and this is the second cell. So this is what we have. Now, the first thing to do is to get what is total EMF. Now, because they are connected in series now, it will be 0.6 volts, the EMF of the first one, E plus E. That's 0.6 plus 0.6, and that's 1.2 volts. Again, we have the total internal resistance. Since it's in series, that should be R plus R. Now that will be 3 plus 3. And that will give us 6 ohms. And now we're going to use our equation. We are giving our capital R to be 5 ohm. So we're going to use our equation now, which says total EMF is equal to I into bracket R plus, here will be R total since it's more than 1. So this will be it now. This one is 1.2 is equal to I into bracket 5 plus total internal resistance is 6. So this will just be 11 I is equal to 1.2. So I will be equal to 1.2 divided by 11. So let's do that. So this is 0.11 ampere. That's the answer to this. Now the next thing we have to get here is to calculate the terminal PD. So that's the second thing, terminal PD. So terminal PD is I times R. The I is 0.11, then the R is 5. This will give us 0.55 volts. The last one is the lost voltage. Lost voltage. Small v, which is I times small r total. And that will be 0.11 times 6. And that will be 0.66 volts. So that's that for this question.